In the last video, I kind of gave a brief overview into some of the terminology commonly associated with frequency response analysis and provided kind of a motivation and reasons to study the content presented at all. In this video, I'm going to attempt to expand upon those ideas a little bit, of course, and present the commonly constructed Bode diagram in terms of how it provides us ways to tune controllers to the limits of their stability, as well as creates the limits of stability parameters neatly for us visually. There's kind of a lot of words. I'm going to talk a little bit about it, and then we're going to jump into the simulations here. You can see all 4 prompts I'm going to go through displayed on the screen right now. I probably won't flash these back up again, just because most of this video will be spent in Colab. Okay, so first, let's talk really quickly about what a Bode plot looks like. A Bode plot is a series of two-dimensional graphs, generally presented in a vertical format, with the primary motivation being a frequency response analysis. Now, what exactly are we plotting on these graphs? Well, there are, of course, the 2 things that we plotted directly in the last video. So first off, we're going to plot our amplitude ratios here. And generally they look like some sort of curve. Now, the other thing we're going to plot is our phase angle phi here. Remember that there is a, sorry, not phase angle, phase shift. I'm going to write that out so I don't forget it. Remember that the critical value that we're looking at right here is going to be, of course, negative pi radians, or negative 180 degrees. This curve may look something like this. And the time here, because, sorry, not the time, the frequency here, we're plotting against frequency. The frequency at which we cross our 180 degree phase shift here is often referred to as the critical frequency. Which gives us a critical amplitude ratio right here. Remember that we want our amplitude ratio to be less than 1 and our phase angle to be less than 180 degrees for our system to be stable. Generally, that's referred to as the Bode stability criterion. And again, amplitude ratio must be less than 1, and our phase angle is going to be less than, greater than negative 180 degrees, or negative pi. Again, this should be, this proves that the system is stable. There's also another criterion, and that is that we only cross the phase angle at one point. We can describe that in future videos potentially, and that'll kind of lead us into the discussion of Nyquist plots. However, for this video, we're going to work with a simple open loop system and assume that we're only going to cross the phase angle once. And I'll prove that to you in a minute for our transfer function when we simulate it here. Let me make sure there's nothing else particularly important to go over here. Okay. Yes. Maximum stable controller gain. So maximum, the Bode stability criterion, right, imply that our controller gain maximum occurs when the amplitude ratio equals 1 and our phi equals negative pi. So that kind of provides us the information we need to go ahead and tackle this process transfer function here. Let me write it down. It's going to be 2 over 12s plus 1 cubed. And I'm just going to write this as big G for right now, because that's probably how I'll end up putting it out. Okay. That's everything here. So let's start to look at this function. We're going to attempt to plot it in a Bode plot. Again, we have a proportional controller right here, so we know that our gain of our controller is simply going to be Kc. So let's go ahead and look at what our maximum stable controller gain will be. So to do that, of course, I have already input all of the rather tedious pieces of the code here. And so the pieces that we're primarily going to use today are our sim function to simulate our system here after we attempt to set a controller gain, as well as SymPy. We're going to use S here, and we should also be using SymPy.lambdaphi. Let me make sure I imported that here. Simplify. I guess we'll see if it works. But SymPy.lambdaphi is going to give us kind of a dummy function with which to work with for our. Let me rephrase that. What it should really be doing here, lambdaphi is going to give us a way to actually do math with our symbolic functions. And so I'll show that to you once we go ahead and import our j omega term. But first, let's start by simply coding our process function in here. So 2 over 12 times s plus 1 to the third power. We said is our transfer function. Of course, our gain is simply going to be our Kc function. And it's screaming at us because we haven't defined Kc yet. Let's just define it as 1 for right now. Actually, I'm going to make it 1.1 just because you never know if 1's going to break something. And so then our total gain here, open loop wise, should just be Gc times Gp. Reminder that we're working in open loop for frequency response analysis. So let's go ahead and input our G as a function of j omega. And that's where we're going to use our SymP.lambdaphi function here. What we're going to do is we're going to plug in omega and then substitute subs. Substitutes an old for a new expression. And so we're just going to tell it, hey, substitute s here for omega times 1j. Omega s. Omega s is not defined. Should be defined. Omega s is not defined. Oh, that's because I didn't define the space in which we're working here. So we're going to go ahead and define a log space here. This is just going to give us a range of frequencies with which to work with. So let's call this, we'll go from -2 to 0 and have 100 steps in there. Perfect. Now, the next thing we're going to do is find our real and our imaginary parts of our gain function here. So we can just say NP real of J, G, J omega, and then NP dot imaginary, looks like image, D, J omega. Yeah, that runs swell. Next, obviously our amplitude ratio is going to be the square root of our the real squared plus the imaginary squared. And then our phi here should just be, we're going to have to unwrap because of the inverse tangent function. And then we should just do NP arctan 2, I think is the one. Arctan 2 imaginary real times 180 divided by pi, and that'll put us in degrees, so it'll be a little bit easier to work with. Okay, so that's all the math. Hopefully it works. So let's go ahead and I'll put this big equals make subplots. Oops, made it. Big dot add scatter. Let's see. X equals our space, and then Y is going to be our M. Mode is going to be lines, and we're going to need to go ahead. Okay, we're going to need to put in rows should be 1, rows should be 2, column should be 1. All right. Hopefully this outputs in the right direction here. So then this should be rows equals 1. Big dot add scatter. Add scatter. Yeah, I think there's an extra thing right there. X is going to be our space. Y is going to be our phase shift. Mode should be lines, and rows should be 2. Go ahead and update our layout. Width equals 600, height equals 400, template equals slightly dark. And we are going to go ahead and recognize that generally a Bode plot, what's it, x-axis? It's x-axis. Update x-axis. X-axis. Okay. What I'm going to do here with this is just simply switch some of these types to log here. Because that is tau. The Bode plot is generally written, and it'll show up a little bit nicer for us here. So should we go to big series, right? Big, and then for this one, I just want to make sure that we can actually see our, we don't need a tab. I just want to make sure we can see our 180 here. 2 equals 1. Maybe I should move this update layout to the bottom. This likes that. Okay. Nope, didn't work. Uh-oh. This is one column. Might just be voting column. Okay. Field plotting. Okay. Okay. So I got an array of 100. 100. Did work through my first line. Probably can. Okay. Actually, let's change some of this around a little bit. Oh, that made it way worse. That made it better. Okay. So as we can see, obviously log scale on our top graph here. Let's go ahead and remove this legend. And of course I did that wrong. Ooh, that was show legend equals false. Okay. So, here we are. We can see here that, let's see, what can we see? So we can see when our system becomes unstable at what frequency. And that's going to be when it hits this negative 180 here. So right at about 0.145 or something like that. 0.145 is the frequency at this controller gain that become unstable. So 0.145, 0.145, so ish. Again, what we're looking for is, sorry, I should go back. So here's our amplitude ratio, here's our phase shift. Right here on this trace, we're looking for negative 180 is our y value. That'll tell us the frequency, that would be the x value, at which our system becomes unstable. At that frequency, we can then move up to our amplitude ratio graph, and we can determine from that frequency at what amplitude ratio we can get to. Now, when the amplitude ratio equals 1, that's when we've hit our maximum controller gain. And so that's what we're going to attempt to do here by kind of shifting around these graphs, is attempt to see what different controller gains will do to our curve here. So again, here at this frequency, kind of the same frequency, right? That 0.145, however, 0.145 is still not getting us past that one value. So let's see what it looks like. 0.145, 0.145 is still 0.7. We can go to 4. And there we have it. Okay, so they're 0.145. We're right at about the 1 value there. So 4 is about our maximum controller gain for this system. And again, that's because that's when our amplitude ratio equals 1, and we denoted that when the amplitude ratio is 1, we can also go unstable as a result of the Bode's stability criterion that we defined earlier. Okay, let me go ahead and look at this next prompt here. It says to simulate the closed loop response of B1. And so that's pretty simple here. I've shown you this simulation function before. And so what it looks like is this. 1 plus t times t. So we have to define our closed loop. And then we're just going to say t and y are simply going to be the simulation results of our closed loop. Lambda t 1, n equals 1,000, and dt, we can say whatever, 0.5, doesn't matter. Okay, so let's do another figure here. Subplots, and just add kind of our simulation results. So add scatter should be what, x equals t, y equals y, and mode equals lines, and then we just got big update layout width equals 600, height equals 400, template equals Bode. Aha. Okay. So let's go back and change this game back down here so we can take a look at it. Okay, so we can see we do have kind of the 3 inverse responses, right? And that's again what we expect because we're in a third order system here. Now, we can see that our process becomes pretty stable here. We're reaching a maximum value of about 0.66, and that's fine. We're not really interested in what the new set is. We're more interested in at what gain value can we make the system unstable. And so again, we set about a gain value of 4 here. And again, we can see that the oscillations are not growing or shrinking in size. And so this point in which our oscillations neither grow nor shrink in size is actually kind of an interesting point of historical relevance. Back in the day with controller tuning, the most popular method was the Ziegler-Nichols method, and the method primarily revolved around, okay, crank it up until your oscillations never grow or die out, and then the gain value at which you've set this here is going to be called your ultimate controller gain, and then your distance between each peak here is going to be referred to as your period. And then from that ultimate gain and that period value, what they did was they said, okay, we can actually determine your controller parameters from that value. And so that's actually the next step here. And what we're going to do, we've found our ultimate gain and our ultimate period. So we're going to use this Ziegler-Nichols method to determine controller gain and reset time for PI controller. And just go ahead and simulate that closed loop response of that controller. So let's go ahead and do that. I'm going to have to pull up my notes here to find my Ziegler-Nichols tuning criterion. So I have my notes right here. The Ziegler-Nichols method. I don't know that I can show this too well to that camera, so I'm going to show this one here. This Ziegler-Nichols tuning method relies on, it's going to be the values on the left-hand side of this table. The right-hand side is another empirically determined tuning method based on the same kind of principle we just had here. Ziegler-Nichols for PI control says that 0.45 times our ultimate gain value will give us our true controller gain, and then our ultimate period divided by 1.2 will give us our integral time there. I don't know if that's going to focus at all, but these are just empirically determined correlations. So again, we determined our ultimate gain was 4, and we determined our period here as the distance between these peaks. So 243-ish minus 199.5 is going to be our period. So then our K should be, or K for our control rather, should be 0.45 times our ultimate gain, and our integral time, or tau I, is going to be 0.83 times our ultimate period. So from that then, GC is simply going to be our generic formula for a closed loop controller, which is tau I times S plus 1 divided by just tau I times S. And then GP should be the same formula as before, so let me type this in, 2 over 12s plus 1 to the third power. Of course, our closed loop then is going to be the exact same thing as the last time. I'll just go ahead and copy that all down and simulate exactly the same as the last time. And so, let's go ahead and plot this out here. Big 3 equals make subplots. Big 3 dot add scatter. Again, we're going to say x equals t, y equals y, mode equals lines, and we don't need to name it. So then big 3 dot update layout with equals 600 bytes equals 400 template equals roughly. Here we are. Okay. And so again, what this does is it just provides us theoretically the most optimal tuning parameters according to a Ziegler-Nichols method. We can see that that looks just about right, because our oscillations go ahead and die out and our controller regains control quite quickly. So, okay, so that was actually part 4 as well, because we went ahead and simulated that closed loop response. So that's all I got for this one. I'll see you in the next one. Bye.